Good morning, class. So I thought we'd get together and I would put a little lecture together for you here and we'll get it posted. This goes along with the two links I sent you on the turbine presentations on YouTube. So just to give you a little heads up, so this material on these turbines, the two turbine videos, and the lectures I record on steam turbines will be covered on your final exam. So it will be at the scheduled time, and it of course will be on iLearn, and it will be similar format to the quizzes that we've been having. So I would encourage you, it will be fairly detailed, and I would encourage you to pay attention to this turbine material. And when you watch those videos, you probably should watch them a couple of times, and I would take notes on them as well, because there will be quite a few specific questions that come out of those videos and this lecture. Okay, so I'm kind of assuming now that you have watched at least a portion, if not both of those videos at least once. And so I'm going to kind of pick up on some of that. I consider that to be kind of background information. We're going to jump into this. I've got a good sized presentation here on steam turbine operating procedures and all kinds of issues that come up. And I think this is, I've used this article for a number of years, and I think it's very, very good. I have put together a PowerPoint on it. So I'll probably send you the article, but I certainly will send you the PowerPoint, which is pretty close to the same thing. I've taken the PowerPoint directly from the article. Just makes for better presentation mode. Okay, so we start out here with steam turbine starting and load changing procedures. So this whole thing is about operation, problems you can get into, damage mechanisms, and that sort of thing on large utility scale steam turbines and rotors and equipment. Okay, so under general objective, what we want to do here is to protect the turbine parts against thermal fatigue cracking caused by internal temperature variations. Okay, the turbine rotor turns out to be the most critical element with respect to thermal stress because of its large diameter. And the idea here, if you take just a slab of steel and lay it on the ground and heat it up, or say you lay it on some sort of a hot bed and it heats up from the bottom, you won't crank any or create any really large significant thermal stresses. In the corners where that thing comes together, yes, there are some stresses generated, but not up close to the yield point because it's unrestricted expansion. The thing is going to grow when it heats up, but as it expands, there's nothing to restrict it. And so you don't generate tremendous stresses. Now, if you take that thing and let's say you rolled it into a circular and made it a hollow cylinder, say you welded the edges together where you rolled the thing up, and then you heat it from either the outside or the inside. Say you're going to heat it from the outside. So it starts off at room temperature, it's very cool. And then you put it into some sort of a hot environment where hot gases are flowing over the exterior of this cylinder, say across it. Then obviously the outside surface is going to start heating up pretty quickly. And the inside, I mean, this thing, you're talking a turbine rotor, could be any place from 8, 10, 12, 15, 18 inches thick. I mean, so this is a tremendously thick cylinder. And it's cold on the inside. So on the bore region, the central hole down the center of it will stay cold for a long time. And so as we heat up the exterior surface, those material elements there try to expand, and they're all expanding against one another. And so that puts that outer surface into compression. And likewise, down on the bore surface of the cold sections of the rotor, that causes tension to appear on the interior sections and down towards the center borehole. And likewise, if the thing was hot and we started cooling it down from the outside, say with a cooling flow flowing over the hot cylinder, then those elements of material on the surface and close to the surface that were cooling down would start drawing back up, and that would cause a tensile stress in the circumferential direction. And so as we heat up a rotor and cool down a rotor, it goes through these alternating stress cycles. If you start cold, go hot, and then cold again, on the outside surfaces, you go into compression, and then you go into tension, and you come back to the same position when everything, say, cools back down to room temperature. On the bore location, down on the inside surfaces, you go from tension to compression. And so, it's an alternating stress cycle. Okay, so that's kind of just general background stuff. It turns out because of its thick cross-section, the rotor is the most critical element with respect to thermal stresses. Stationary parts in the casing and around the turbine are smaller radial thickness, and in general, they have more forgiving geometries, and so they allow for a larger degree of unrestricted expansion. And so they see lower thermal stresses compared to the rotor. So if we design operating procedures to protect the rotor itself from thermal fatigue cracking, it will also protect the remaining stationary parts of the turbine. Okay, so the specific objective of starting and load changing procedures is to provide for a selected number of thermal cycles of general turbine operation before the appearance of fatigue cracking. So it's not if we're going to cause cracks to appear in this rotor, it's how soon are we going to cause cracks to appear, a detectable crack. Operating at conditions which result in less than the desired number of cycles fatigue capacity accelerate the accumulation of thermal fatigue and result in earlier initiation of cracks. So basically the way this goes is if we heat it up and cool it down faster than we should, we allow the thermal stresses to go to higher levels, both on the compression and tensile side, which means the alternating stress cycles get larger, and that eats up the fatigue capacity of the material, and we get cracking sooner. So by controlling our ramp rates and how we operate this thing, we can extend the useful life of the rotor. Rotor cracks appear typically in fillets, radii, blade attachment grooves at the rotor surface as shown. I've got a figure coming up here on the next slide. Once initiated, cracks generally propagate slowly. In general, they don't grow quickly, but under certain conditions, we can get catastrophic failures, and that's one reason that we're so concerned about this. 1974, Gallatin, Tennessee had a rotor burst on cold startup, and this, several thousands, I don't know how many tons of material, but this thing came apart during operation, and parts of the rotor penetrated the inner casing. The outer casing went through the roof about 100 feet up in the air and landed a quarter mile away in the parking lot. So there's such a tremendous amount of energy here. These failures are just unacceptable. That particular case, there was no loss of life, which was truly a miracle. And the last bullet on this slide talks about crack removal by machining. So if these small micro cracks or very small cracks are detected early enough, a lot of times they can be machined off during an outage when the rotor is taken out. And basically, with the crack gone, so long as we have enough cross section to withstand any operating stresses, then we can basically heal the rotor, or we can restore fatigue capacity to a rotor by machining off very small cracks in the early stage of initiation and growth. Okay, so this is just a kind of a cartoon cross section of a steam turbine rotor that's you know, if you've watched those videos, you have a really good idea what this stuff looks like. So I don't really have too much to add to that. That's just, there is stress concentration regions primarily is where you see those things initiate. Probably more on the surface than the bore, but the bore connected cracks are harder. You have to take the machine apart to find them. And so they're much harder to find and probably more dangerous in the long term because of the difficulty in knowing that they're there. Okay, so this illustrates, I kind of talked through this, I guess, a little bit out of sequence on the first slide, but this shows what happens. Say we had a cold, that's a cross section of a rotor, and that's that slab that we rolled up and, welded the ends together to make this thick wall cylinder. And so you see the stress profile coming out on the right there as we heat the surface, and we're assuming we're heating it uniformly all around, and the base material is cold. And so you see that on the outer surface, we get a huge compressive stress, and then it declines as we go deeper into the body of the material, and then it switches from compression to tension and winds up with a fairly significant tensile stress at the inside of the bore. And so if there's a crack located there, then during this cold start where we're heating from the outside surface, that tensile stress is trying to pull that crack apart. And if we get to, in your fracture mechanics, if we get to a critical crack size and the material properties are not good, then this whole thing can let go. And it doesn't happen often, but it does happen. And so there's lots of guidelines to try to avoid that type of failure. Changes in blade path steam temperature will produce thermal stresses in the rotor, which persist as long as there is a difference between the surface and interior temperatures of the rotor body. So it's that temperature profile, that difference, that causes this differential expansion. And say this is not free expansion, it is restrained by the geometry itself. And that's what causes the stresses to be so high. Okay, let's see, thermal stresses on turbine rotors. Such a temperature difference exists, so we get these temperature differences immediately following a rapid change in surface temperature because of the time required to heat the flow from the surface to the interior. So this is a big thick wall cylinder, and you just can't equalize temperature very quickly. If you had a thin wall cylinder, you would not have this problem with thermal stresses, but you wouldn't have enough strength in the section to generate any power, so that wouldn't work. Stress is proportional to the temperature difference and is greatest at the rotor surface. We saw that from the diagram. It's a transient stress because it ceases, and that's not spelled right, but anyway, ceases to exist when the surface and interior temperatures have equalized. So over a period of time after we operate this thing for a while, the entire rotor body will come up to pretty much the same temperature, and then the thermal stress disappears. I have a figure here that shows various steam and rotor metal temperature relationships that may exist during a starting period. And so here we go. So you can look. So up here at the top, we have the temperature of steam to the throttle valves, okay? And notice that as load increases, as time increases, this temperature increases. We'll talk a bunch about this later, but this was a boiler characteristic primarily. And so when you get up to higher steam loads, the boiler can produce the 1,000-degree steam that we're basically designed for, but at low flows, not so much. So this is starting out showing about 750. You know, it's going to depend on the particular boiler, but it's going to be much less than, you know, when we get up here, you know, I don't know what percent load that is, what, 60% load or something like that. We finally hit our peak, our desired steam temperature back here. So if you were starting up this unit and it was still hot, maybe it's just been off for, you know, overnight where we didn't need that generation, that rotor might still be 900, 950 degrees. And if we're going to hit that with 800-degree steam, we're going to force cool it. And that's going to cause a potential for great damage. So that's where we're going in this. You see, this is when we first start rolling the turbine with the steam. So this is just almost no steam flow, and we slowly ramp up. And then we get to synchronization. I've got a little video I'm going to show you here in just a second as part of this presentation. But that means that we have electrically tied to the grid. Before you synchronize, the unit is simply, you're turning the generator, but it's very low level and you're absorbing any electricity generated internal to the station. So that unit doesn't have to be tied to the distribution grid. This is operation at 5% load. As you know, time goes on, we get the steam temperature starts to come up. And then these are three different, well, two different locations in an average. So this is the interior surface of the bore. There's very typical to have this borehole down the entire length of the rotor. And this is the temperature on the rotor surface, and this is the impulse chamber, which again, that's defined very well in those other two videos I want you to watch. So at any point in time, this is the temperature difference across this thing. And so that's the temperature difference that's going to potentially cause thermal stresses to exist. And then as time goes on, we say this levels out, and this eventually will work its way up to be very, very close to the 1000. And this just shows how the average temperature increases, just kind of halfway in between these two. Okay, I think I'll stop this right now or pause this presentation, and we'll go to this discussion of synchronization. So here's our man. He's pretty good. So let's see if I can get this. I think this will record right into this Zoom video if I play it. This is 3 minutes and 27 seconds.
So let's now turn our attention to synchronizing. When the generator is switched into the power system, it is not sufficient to just close the circuit breaker. Certain definite conditions must be set up before the generator can be synchronized to the system. The first thing is that the generator must be running at its rated speed. This is done by adjusting the governor set point. Second, the generator terminal voltage must be adjusted to equal that of the bus to which it is being synchronized. This is done by adjusting the excitation. As the strength of the magnetic field is increased or decreased, so will the terminal voltage rise or fall. The third very important factor is that the incoming generator voltage must be in phase with the bus voltage. What do we mean by this? Well, look at this example showing one phase only. Here is the sine wave representing the bus voltage, and here, superimposed, is the incoming generator voltage. You can see that the generator is over 90 degrees out of phase. If we closed the breaker in this situation, the generator would attempt to pull itself into phase. Now, this could twist the windings in the stator core and create considerable damage. Of course, the great surge of power would be detected and the breaker immediately opened by protection devices. In order to provide the correct conditions for synchronization, we need to very gently adjust the speed of the incoming generator so as to bring it into phase with the bus. At the moment that the two are in phase, the breaker should be closed, and the unit will then lock into synchronism with the power system. On most modern units, this synchronization is performed automatically. However, you may find the need to do this manually on certain occasions. For this purpose, a synchroscope is provided. This is connected to either side of the breaker and, in fact, indicates the difference in phase between the two sides. For example, this condition shows that the generator is 90 degrees out of phase with the bus. As the pointer is stationary, it also indicates that the speed, that is the frequency, of both the system and the incoming generator are identical. More often than not, you will see the pointer slowly rotating like this, indicating a slight variation in speed. In the case shown, the incoming generator is running slightly faster. If the rotation is slow enough, you can manually close the circuit breaker just before the pointer reaches the midnight position. The machine will then lock itself in synchronism and start providing power. In order to further increase power output, it is necessary to add more torque to the unit. This is done by increasing the steam flow to the turbine. But can we not also increase real power output, that is megawatts, by increasing excitation? The answer is a definite no. Increasing the excitation will only increase voltage to a certain extent and will also increase the reactive power output of the generator. We'll be talking about this later. So let's now turn our attention to synchronizing. When the generator
Okay, so that's probably a better explanation than I could have given of synchronizing a unit to the grid. So let's move on. Okay, so thermal stresses in turbine rotors, heating of the rotor followed by an equal cooling, as shown in this figure 4, constitutes a thermal cycle. I mentioned those previously. It imposes on the rotor a cycle of alternating stress. And the rotor material has a limited capacity for withstanding stress cycles. And so you see, this is similar to that previous, I guess. So this is a temperature on the outside on the OD. This is the bore temperature, and this is the average. But so you see, we're heating up here, so this surface would again be in compression, and then everything kind of equalizes, and then when we cool down, the surface would go into tension until we got back down to where we started. Likewise, the bore surface will do the opposite. Okay, so cracks are going to ultimately develop after a number of cycles, and the number of cycles before the crack is determined by the severity of the stress. Relationship between alternating stress and cyclic capacity is a material property. It's possible to predict the number of stress cycles necessary to initiate a crack in a kind of a general research sense, but you can't predict this exactly, but you can get a good indication. You can get enough information to tell you how you want to operate the particular turbine or rotor. For a particular temperature change, the greatest thermal stress is developed when the change is made instantaneously. So, I mean, the way this works is, let's say we're at 50% load and we're going to go to 100% load. Well, this will cause a warming, an increase in steam temperature, most likely, which will cause a warming of the rotor, which then will cause stresses. And so the operators know they have thermocouple readouts on the actual temperature of the rotor at the high pressure and intermediate pressure in different locations. The thermocouples are in the casing, but they're very close. And by experimentation and experience, they know they can very closely estimate the rotor temperature based on these thermocouple measurements. And so they know the temperature where they are, they know what they're going to go to, so they know the delta T that the transient is going to cause. And then it's a question of how long is it going to take them to initiate that transient. And of course, the bigger the delta temperature change, the longer period of time they have to take to initiate the change in order to control the thermal stresses. For a particular temperature change, that should say change, sorry, the greatest thermal stress is developed when the change is made instantaneously. That's the most potentially damaging way. But if it's a small temperature change, then that's not necessarily a problem. If it's a large temperature change, that could be a significant problem. So the stress can be considerably reduced by accomplishing the change over some determined time period. Lengthening thermal transients will increase the number of stress cycles available for initiation. If you lengthen the amount of time it takes to do the transient, then you reduce the thermal stresses and you get more stress cycles before initiation. For large temperature changes, the stress can be limited to any desired level by choosing an appropriate time period. So we can manage this. We simply have to be on top of it and pay attention to what we're doing. Okay, the criterion for determining starting procedures is the temperature of the high pressure and or intermediate pressure turbine metal before admitting steam to the turbine. Cold start procedures are to be followed when the initial temperature of either the HPIP rotor metal is below the material fracture appearance transition temperature, the FATT. Okay, so now we need to have the FATT discussion. Well, luckily, I have another brief YouTube video that discusses what FATT is. So we're going to jump to that. All right.
Hi, Dr. Lyons here, of course. This video discusses the ductile to brittle transition in metals, which is really very, very cool. The Liberty ships were built during World War II primarily as cargo ships, although some did also carry troops. The U.S. built over 2,700 Liberty ships. A problem developed with some of the early ships. These broke in half without warning, and sudden catastrophic fracture is called brittle fracture. In the investigation of these failures, a few things were noticed. One was that the ships tended to be in cold water, and the cracks originated at stress concentrations. There was some sharp corner or edge that initiated the crack, and once the crack initiated, it propagated around the entire girth, and the ships actually separated into two pieces as shown in this figure. So this is related to a property of some materials called the ductile to brittle transition temperature. Pure metals which have a transition temperature tend to have a very definite transition temperature called TDB. At temperatures greater than the ductile to brittle transition temperature, the material is ductile. And at temperatures below the ductile to brittle transition temperature, the material is brittle. Iron and other BCC metals tend to have a ductile to brittle transition. Almost all HCP metals have a ductile to brittle transition, but face-centered cubic materials tend to not have ductile to brittle transition temperatures. They tend to remain ductile at all temperatures, at least known to us. Now, when we alloy the metal and create a solid solution or other type of alloy, the transition temperature tends to not be as uniquely or discretely defined. The transition tends to occur over a finite temperature range rather than a specific temperature. The most common way that the ductile to brittle transition temperature is determined is with a Charpy impact test. And this slide shows a couple of images of the test specimen. It's a little sample that's a couple inches long, and there's a V notch that's cut into one edge of the sample, and that forms a stress concentration. The test specimen is put in an anvil in the test machine. The little white bar right here is the test specimen, and it's supported at both ends. You can see that in this schematic right here, the test specimen is supported by both ends, and a hammer is raised and swings down and hits the back of the specimen, causing it to fail from the notch. So it's an impact bending test with a notch in it. So here we see an actual test specimen viewed from above in the test fixture, being supported at the two ends, and the impact force comes in and whacks it right behind the V notch. Now, in terms of the test machine up here in the upper left-hand corner, the main components are the anvil, which supports the sample, the hammer, which impacts the sample, and a scale and a pointer, which is used to measure how much energy is absorbed. The hammer is originally raised to a height h. If there's no sample, the hammer will swing down and then back up to the same height h, assuming this is a frictionless bearing here. When you put a sample in the way of the hammer, then energy is absorbed by the sample when it breaks, and the more energy that is absorbed, the lower the final height h2. So if the sample didn't break at all, then all of the energy in the hammer would be absorbed by deformation and vibrations in the sample, and the height would be 0. And if very little energy was absorbed, the hammer would whack the sample, hardly slow down at all, and swing up to a fairly high height. The scale would indicate the amount of energy that's absorbed. These two pictures that I've just added show what a sample looks like if it's failed in a ductile mode on the left and a brittle mode on the right. In the ductile failure mode, we have a lot of deformation in the sample around the fracture, and all that plastic deformation absorbs energy. In the brittle fracture mode, you get cleavage from the fracture with very little deformation in the sample. Sample just breaks. Now, the absorption of energy during plastic deformation that's associated with ductile failure is going to result in a high measured impact toughness. So we'd be up here in the top right part of the toughness versus temperature curve. At a low temperature, the sample may be brittle and low energy absorption, and we'd be down here in the brittle temperature range on this chart. So the transition temperature is going to be somewhere between the temperature at which it's ductile and the temperature at which it's brittle. Here are some actual test results for some iron alloys. And we'll start with the graph on the top. And this chart shows impact energy versus temperature for plain carbon steels with different amounts of carbon. And here we have a low carbon steel. The ductile to brittle transition temperature is around -50 degrees C. So low carbon steel is going to be ductile over the general operating range for most mechanical engineering structures. And as we alloy the material with increasing amounts of carbon, the transition temperature increases. So here at 0.2% carbon, the transition temperature is somewhere around -10 degrees C. Here all the way up at 0.8% carbon, the transition temperature is around 150 degrees C. So the 0.8% carbon steel is going to be brittle at ambient temperatures because in its ductile to brittle transition temperature is around 150. So it's not going to become ductile until elevated temperatures are reached. So as the amount of carbon is increased in plain carbon steels, the ductile to brittle transition temperature increases. You can see also the transition broadens. Essentially, it's broadening because the material is becoming more brittle at elevated temperatures. Other alloying elements have a different effect. The bottom chart shows how the ductile to brittle transition changes with increasing amounts of manganese. Here in this iron carbon manganese alloy with 0% manganese, the ductile to brittle transition temperature is around, say, 120 degrees C. And as the amount of manganese increases, the ductile to brittle transition temperature decreases. So which is better, to have an increase in the ductile to brittle transition temperature or a decrease in the ductile to brittle transition temperature? But generally, you want a low ductile to brittle transition temperature so that the material will be ductile at your operating range. And if it's ductile, you'll have some warning before it fails. If it's brittle, the sample or the machine, the part will look fine until it fails. So you can see that the actual shapes of the curve depend on the specific material that we're talking about. And that has led to different definitions of the ductile to brittle transition temperature. The ductile to brittle transition temperature can be defined as the temperature at which the Charpy impact energy is the average of the upper and lower values. And that's what's illustrated in the figure on the right. The lower impact energy is about 25. The upper impact energy is about 85. And the average is around 55 or 56 degrees C. Another definition that has been used in reporting data is that the ductile to brittle transition temperature is the temperature at which the Charpy impact energy has dropped by some percentage of the upper value. Some data will be reported as the temperature at which the fracture surface appears to be 100% ductile. So the result, or the reported value of the ductile to brittle transition temperature, actually depends on the definition. So that's something that's important to know when you're selecting materials for a design. So that includes.
Okay, guys, I will send you the links to those videos so that you can watch them. So that ductile to brittle transition temperature is what we call in the power industry the fracture appearance transition temperature. So the way they talk about in the power industry literature is they break those Charpy impact specimens at different temperatures, and then they take a microscope and they examine the fracture surfaces. And the temperature at which the fracture surface is about half cup and cone and about half cleavage. The cup and cone would be is what they call the ductile fracture. It's like you take a piece of taffy and you pull it for a while until it finally breaks apart, versus a cleavage type fracture. If you drop a piece of glass and it just shatters, it's very brittle, you get the cleavage type. So the temperature at which we get 50% ductile, 50% brittle is called the 50-50 FATT, and that's typically what's used in this discussion on turbine rotors. Now, if you read a different paper, you need to read for the transition temperature and how they are determining it for that particular paper. But in my experience, it's usually the 50-50 in terms of the appearance of the fracture surface. Another issue that I'll try to dig up another little video on embrittlement. When you buy a new turbine and turbine rotor, the manufacturer will take some of the scrap material and test, do a number of tests and tell you what the FATT is for that virgin material on that rotor when you buy it. And it may be, so say it's 275 degrees, something like that, which would be typical. These typically run someplace between 250 and probably 350. And so you operate this rotor for a while, but over time, this transition temperature, this material can embrittle, which will raise the transition temperature. So if you're working on a rotor that's 15 years old, you may have the original purchase numbers in the file, but you don't know what the actual FATT is after 15 years of service. There's what they call thermal embrittlement and hydrogen embrittlement and all this sort of thing. So I'll put that discussion off until I see if I can find a little YouTube video that does a better job explaining it than I can. The other thing would be that relates to what we just saw is the typical rotor steels are 1% chromium, 1% molybdenum, and 1/4% vanadium. So it's called 1% CR, 1% MO, and 1/4% V, vanadium. And so it follows those curves, lower shelf transition to the upper shelf, like some of those that he showed for the carbon steels in the video. So this is right in our wheelhouse in terms of operating a steam turbine. Okay, hot start procedures are to be followed when the initial temperatures of both the HP and IP rotor metal are above, comfortably above the material FATT. So there's no doubt that the rotor will react, the material will act in a ductile sense in terms of cracks, crack propagation, crack growth, resistance to thermal fatigue and other stresses. And I mentioned this, but thermocouples typically installed at appropriate locations to provide the temperature indication to determine the type of starting procedures to follow. Basically what they do is they drill through the casing to the point they're almost just about 1/4 of an inch away from bursting through that inner casing. It's a pretty small hole, just enough to feed a thermocouple down, and then they'll put some sort of thermal fluid in there to transfer heat effectively, and then immerse the thermocouple in it and push it all the way down. So that thermocouple is really on the stationary side, opposite the location on the rotor that you're interested in knowing the measurement. Studies have been done. The Electric Power Research Institute has actually put thermocouples on the rotors themselves and put telemetry equipment to transmit out the signals. And so there's a good bit of information on knowing how to install those thermocouples so that they give the appropriate readings. That's not really an issue today. Okay, various cold start procedures may be employed in order to control the warming up of the turbine inlet valving and other components from an initial cold state before we synchronization of the unit to the line. So you now know what synchronization is, where we tie to the grid. And there's different recipes, different formulas for doing this. One such procedure is to roll the turbine with steam to approximately 2/3 rated speed, and then hold at this speed until the high temperature rotors have warmed throughout to above the material FATT before reaching full speed and putting it online, where you would have additional stress put on the rotor. And that's to avoid the hazard of brittle fracture by limiting rotor stresses. For fossil units, main steam at the turbine inlet at rolling should have preferably 100 degrees of superheat to avoid the high pressure turbine operating with a high percentage of moisture in the exhaust end stages. So we want that 100 degrees of superheat so that we don't have excessive moisture coming out the end of the high pressure turbine. The inlet temperature should not exceed recommended limits to avoid internal shocking of rotor surfaces at the inlet region with too high of temperature. So you want 100 degrees of superheat, but you don't want to go too high, or you can shock the components. Pre-warming system. Another method of cold starting is to use a pre-warming system in which auxiliary boiler steam or station steam from another source is admitted to the high pressure and IP intermediate pressure turbines before opening the turbine main steam reheat valves to admit steam from the boiler. The units kept on turning gear, and that's that gear, and there's really not that large a motor. It's surprising. I think it's like, I don't know, a 50 horsepower motor or something can turn all of the turbine rotors to keep them moving around when they're hot, so you don't put a permanent set in them. So we keep the unit turning slowly on turbine gear, controlled speed while turbine components are being pre-warmed and while the boiler is being fired. There's a little picture of a system on the next slide. Pre-warming steam on this one is admitted to the cold reheat or high pressure exhaust and regulated to pressurize the high pressure element to a prescribed level. We crack some drain lines to get a little bit of a flow. And the system may provide the necessary warming to bring the high temperature rotors to above their FATT or be used to shorten other rotor warming soak periods. And this is a little bit confusing. I've never really liked this, but basically down here at the bottom, we've got warming steam from some auxiliary source, and they got a shut-off valve. We come down here, so this is warming valve A, and then we come over here. Let's see, where's warming valve? This is warming valve V, so then this line connects in over here, and so we can put steam in here. So I guess if we're going to put it in here, we don't have to put it in there, but we can then, so that this would be shut, this would be open. We would open this, and then so we can feed it down here and here and put it in here and then let it come out the drain valves. So anyway, that's what the pre-warming system is about. Once the high temperature rotors have been warmed above their FATT, the term is accelerated rated speed, synchronized, and initially loaded to whatever the prescribed minimum load would be. Okay, I think I'm gonna stop here. I think this has probably run long enough for this one. And so we'll pick up here on the next recording on warm and hot starts. So I'm going to cut this off, get it posted, and I'll be back in touch soon.